So good afternoon everyone. Today is the 11th live class on numerical methods for engineers and we'll get started. So today we're going to discuss two major topics. One is the predictor corrector technique and why we use it, how do we use it, when we use it and so on. And the second topic we're going to discuss is stability. Okay. So let's get started with the predictor corrector technique. So, as in the previous weeks, we have seen what happens in explicit technique, what happens in implicit technique, and so on. So, you must have noticed that there are few, sometimes what happens is when we are using the explicit technique, the solution quite diverges, a predicted solution quite diverges from the true solution. Okay. So a lot of reasons can be there, as we have been seeing from the very first class of linear and nonlinear equations as well, that a lot depends on the initial conditions that we are taking. Okay, and from the initial condition, how the next guess is evaluated and so on and so forth. And does the guess that we keep on evaluating merge to the true solution, or they diverge away from the true solution? Okay. So predictor corrector is one of the techniques which uses both explicit and implicit techniques at the same time, and tries to give a better prediction of the answer or the guess or the true solution. Okay, so we will go ahead with this class. So what basically happens in predictor corrector technique is that it uses okay, so the issue over here is that we know one issue is that in explicit techniques it quite diverges from the true solution. One major issue with the implicit technique is that they use these iterative solvers, so we have to keep on doing it again and again and again to get the answer, right? So we are highlighting one of the issues of the implicit technique over here, that implicit techniques for nonlinear equations involve these iterative solvers. Okay, so one way to avoid iterative solvers is to use predictor corrector techniques. Okay, so first let's look at first order predictor corrector technique, and why first order we'll understand it at the end of this derivation. Okay, or derivation of flow to understand this technique. So the first step in predictor corrector technique is that we use Euler's explicit technique to estimate the value of yn plus 1. Okay, and in this step what we actually do is we predict yn plus 1, and we do not assign this yn plus 1 as the ultimate yn plus 1, but we tell it as some kind of a yn plus 1 bar. Okay, because this is using the explicit technique, right? And initially we stated that in the explicit technique there are like it sometimes diverges from the true solution, or it is not so accurate as the implicit techniques. Okay, so first we make a prediction with the help of the Euler's explicit method, and we use this formula: yn plus 1 is equal to yn plus h times f of yn. Okay, so once we have computed this step, the second step in predictor corrector, so we have predicted, this step is for predicting. Okay, so I'll just write this step is prediction. Okay, the next step is called corrector, that is predictor corrector, so basically correction. And what do we do in this step is that the value that we had obtained from prediction, right, that is yn plus 1 bar, this value that we had obtained, we use this value and we again predict a value of yn plus 1. But why do we state it as the corrected value? Because we are using the predicted value of yn plus 1 in order to get closer to the actual yn plus 1. So this formula basically uses, so then what we do is we basically correct the estimate or correct the prediction that we had made by using an implicit technique, and in this case I'm using the trapezoidal rule for the ODE IVPs. Okay, and the formula that we write is yn plus 1 is equal to yn plus 1 is equal to yn plus h by 2 times f of yn plus f of yn plus 1 bar. Okay. So these are the two ways, two formulas. So first we predict it with the help of Euler's explicit technique, and then we correct it by using the implicit trapezoidal method. Okay. So let's see an example how we are actually supposed to go ahead with this predictor corrector technique. So we will apply this first order predictor corrector method to integrate a very simple example, that is dy by dt is equal to 5 pi. Okay. And here the initial condition that is given to us is y of 0 is equal to 1. And we are trying to compute this from t equal to 0 to t equal to 0.05, where the h value that we have is basically 0.05 itself. So one value at t is equal to 0 is known, and just at the next stop we are supposed to compute the value of y. Now, since we have used a very simple equation, a differential equation over here, the analytical solution of this differential equation is going to be y is equal to y naught e to the power 5t. Okay. So since y naught is given to as 1, it reduces to e to the power 5t. Now, if you use that analytical expression to compute the required solution, that is y of t is equal to 0.05, y at t is equal to 0.05, the exact solution that we will get is this 1.2840. Okay. Now let's see, using the predictor corrector method, what are we able to get? So as we said, in the predictor corrector method, what we will do is first we are doing a prediction. Okay. And in this prediction, what we are doing is we are computing the value of yn plus 1, but we label it as yn plus 1 bar is equal to yn plus h times f of yn. And the value of yn is given to be 1 plus h is given to be 0.5, and f of yn is basically 5y, right? So 5 times y is given to be, y naught is given to be as 1. So we calculate this and we get yn plus 1 as 1.25. So after you've got the prediction by the first step of this method, you can go ahead and compute the error. Now the true value was supposed to be 1.2840, and what we have got is 1.25. When you take the mod of the error, modulus absolute value of the error, you get 0.034. Now, that is quite an error. Even till the second place of decimal, we have the error, right? So let's go ahead and use the second step, that is the corrector step, and see how close are we coming to the actual solution. So here again, using the trapezoidal rule, for the implicit technique, we write the formula yn plus 1. So this is going to be the correct estimate and nearly close estimate, and this we won't be labeling as bar. Okay. So yn plus 1 is equal to yn plus h by 2 times f of yn plus f of yn plus 1 bar. Okay. So now you put in all the values, that this value was given to you as 1, this is 0.5, and this you just computed 5 into 1. And this is going to be 5 into the y value that you had predicted, that is 1.25. Okay. Now you get the new value of yn plus 1 as 1.2812. Now you again estimate the modulus of the error and you get it as 0.0028, which is more accurate than it basically reduces even to the next place of decimal. So we even get a more accurate answer. Okay. So now you see, just by Euler's explicit method what we were getting, and simply by using implicit what we would get. But if we use this predicted value from Euler's explicit and use in the Euler's implicit method or the trapezoidal rule, how close do we get to the actual solution that the error reduces to 0.02, 0.0028. Okay. Okay. Now, it does not need to stop here. This can be further continued in this form. That is, let's say the value that we have obtained from the first correction is this, right? So yn plus 1 c1 is the first value that we have obtained. Now we can also continue this and calculate c2, and c2 is basically going to be, this value is going to remain the original yn. This is also going to be same, but this value is going to be whatever you have found out in the correction, the first step in the corrected value. Okay, that was 1.2812, right? Now, so this is the answer that you will get when you do perform this corrector step the second time, and you see that the error has even more reduced to 0.0012 from initially what was the error? It was 0.0028. Okay, and it goes on decreasing this way. So thus values can be successively improved. Okay. Now, why was this called the first order predictor corrector technique? Because the formula that we had used here was the first order Euler's method, or first order explicit Euler's method, and this was also the first order of the trapezoidal rule. So when we are using this explicit and implicit first order methods for the predictor corrector technique, it becomes the first order PC technique, predictor corrector technique. Okay. Now, as the orders increase, here I have kept an example of the fourth order predictor corrector technique, where we use fourth order Euler's explicit method and fourth order trapezoidal rule. Okay, where the formula is going to be the predicted value of yn is going to be yn plus h by 24. So this formula has been derived from, again, the same kind of derivation as we have learned in the previous classes. So I've just written the formula here for you people to understand that how exactly it proceeds. So here it's 55 times 55 times f of yn minus 59 times f of yn minus 1 plus 37 times f of yn minus 2 minus 9 times f of yn minus 2. Okay, sorry, this is n minus 2, this needs to be n minus 3. Okay, so what basically is happening here, if we just take a moment to have a recap. So these are the slopes, subsequent slopes, as we can call this, and this. These are all the slope values. Okay, and whatever number is multiplied here is for us to take the weighted average of these slopes. Okay, so that we can get to the closest value of the prediction of yn plus 1. Now, in order to compute the actual value of yn plus 1, what we will basically do is use this predicted value that we had done in the previous step and compute the actual value of yn plus 1. Okay, so this was your fourth ordered predictor corrector technique. Now we will move on to the second important topic for today, that is stability. Now this particular topic, stability, we had come across in our previous classes when we were discussing that is a particular method stable or not. It basically means that when a particular numerical technique is being used for evaluating the true solution, evaluating the predicted or approximate solution, how does that particular technique help us to converge at at or close. It doesn't happen at the true solution or close to the true solution. So while these numerical techniques are being used, we had seen a couple of cases in the nonlinear numerical method technique class as well, that some of the times what happens is the solution starts along the lines of true solution itself. I mean, the proximate solution that the numerical techniques predict, they start along the true solution, but they diverge a lot from the true solution as the time step increases. Okay, as we decrease the time step for even a certain instant of the independent variable, it will stay constant, I mean close to the true solution, but again it might diverge. Also, based on the initial value, how do we start a particular this thing, the initial guess that we use also determines whether the subsequent guesses are going to merge at the true solution or it is going to diverge from the true solution. Okay, so in this part of the discussion, we are going to see the term stability in a more formal manner, so as to understand how do we exactly compute the stability, or understand whether a particular technique algorithm is stable or not. So the aim in this part is basically to determine whether a given algorithm that we are using to determine whether a given algorithm that we are using to solve an ODE IVP is stable or not. Okay? So we've seen that Euler's explicit method can be quite unstable, and even in implicit methods, they are slightly more stable, but they require these iterative solvers and so on and so forth, right? So there are two different ways in which solutions can be incorrect. Okay, so when we are trying to study the stability, one of the important things that it's necessary for us to understand is that how can we even go wrong, and hence understand whether the solution that is not matching with the true solution, and hence the technique might be unstable. Okay, so how do we even go wrong while we are using these numerical techniques? Sometimes what can happen is that we might get spurious solutions. That is, so we won't understand the meaning of spurious solutions right now, but when we do go along this class, I'll show you what are actually these kind of solutions. So they basically mean that the solutions are not true at all. They are like some random values, but they are not true at all. Okay. And the second type is when we get numerical errors. So we have the solution, but the solution is not completely merging or is not enough close by to the to the true solution. But there are some numerical errors that keep accumulating as and when the subsequent guesses are being evaluated. Okay. So in today's class, we are going to focus on what are these spurious solutions and how do we understand whether a technique is stable or not based on these spurious solutions. Okay. So let us consider the general form of let us consider the general form of an ODE IVP solver algorithm. So till now we have seen so many solver algorithms, right? But let's consider the general form over here. So that can be written as yn plus 1 is equal to alpha times yn plus 1 plus alpha 1 times yn. Just notice here that these yns are decreasing, yn plus 1, yn, then yn minus 1, and so on. And a particular number, alpha naught, alpha 1, alpha 2, dot, alpha k, has been multiplied with the y's over here, plus the time step h times beta naught, beta 1 and dot 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 beta k has been multiplied with the function values, this y dashes, y dash n plus 1, y dash n, and so on and so forth. Okay. Now, let us apply this to the simple ODE. Let's consider a simple ODE over here. That is dy by dt is equal to lambda y. Okay. Now say that alpha naught is equal to 0, which is in almost all the cases alpha naught, the value of alpha naught is 0, and hence these equations are mostly written as yn plus 1 is equal to something yn. This term is mostly missing because the value of alpha naught is 0. Okay. So let's say that y of alpha naught is equal to 0, which is true in most of the cases. Hence, this expression is going to reduce to yn plus 1 is equal to alpha times yn plus alpha 2 times yn minus 1 plus so on and so forth, plus the time step times beta naught. And what we are going to do here is that we are going to replace the values of y dashes, y primes with lambda y. Okay. So you are going to replace it, and we are going to end up with these terms now. Okay. After we end up with these terms, just take this side, the one on the LHS to the RHS or vice versa, whichever is easier to understand, and equate to 0 on one side. And on the other side, take whatever comes inside the bracket, and our aim will be to take common these values yn plus 1 or yn minus 1 or yn minus k plus 1. Okay, and let's label this for the timing as equation 1. Now this kind of an equation is important for us because this is called as a difference equation, or more precisely a linear difference equation. Okay. Now we know that the initial condition, say y naught is equal to c, let's assume something over here, and because dy by dt is equal to lambda y, that demands that y proceeds exponentially, y basically increases exponentially with time, is what is given by the physics of this equation, right? So now let's assume some terms over here. That is, let y1 be written as c times mu. Okay. Similarly, y2 will be written as c times mu squared, and y3 will be written as c times mu cube, and so on. Hence, yn plus 1, yn, and yn minus k plus 1 is going to be reduced to this format. Let's not go to that for now. It's going to be reduced to this format. Okay. Now what we will do is we'll just rearrange this term mu in such a way such that we get again a common term outside, that is yn minus k plus 1 outside, and c as one of the common terms. And what the new thing that is going to be, the variable thing that is going to come up in every step is basically the mu k and mu k minus 1. Okay. Substituting this into the equation 1 that we had written earlier, we are going to get something like this, where what have we done? Let's go ahead and just draw a connection. What have we basically done? We have replaced these values of yn plus 1. I've not changed anything else. These and all are constant. These all bracketed terms remain the same. The only things that we have changed is the values of yn plus 1, yn minus 1, and so on. Okay. So that makes it these values. So only these values have been changed, but all others remain the same. Now this equation is known as the characteristic equation of the multi-step algorithm. Okay. Now this has k roots. If you can, if we can visualize this has k roots, and the roots are mu1, mu2, and so on until mu k. Okay. Now the solution of this difference equation that we had written in the equation 1 is given by yn plus 1 is equal to, so this is the general form of the solution, c1 mu 1 to the power n plus 1, c2 mu 2 to the power n plus 2, and so on. Okay, but take a moment and understand the step over here. That is, it tells us that this particular algorithm, I mean the derivation that we have been doing, that tells us that there are unlimited roots like this, that is c1 mu 1 to the power n plus 1. So basically all these are roots, right? Mu 1, mu 2, mu k, and so on. But the ODE IVP that we had written, it was just dy by dt is equal to lambda y, right? But for this ODE IVP, the solution, analytical solution, is y is equal to y naught e to the power lambda t, and this has just one single exponent. So, but this so single exponent, so there should be just one single mu over here, which is supposed to be the root. Okay, but this equation is showing us that there are multiple roots, right? So only one of them is the true or closest to the true value, the root, closest to the true root, but the all others are false roots, or these are called as spurious solutions. And hence, in this way, spurious solutions can exist. But in such a case, what happens is, still this particular algorithm can be used to evaluate the solutions of the ODE IVP if the mu value, which is actually the true mu value, is greater than all other mu values. If that happens, then this technique can still be used. And it is important to realize that the value of this mu basically depends on this h lambda value. We will see in a graph how it depends on the h lambda value. And these alphas and betas are basically technique dependent, whichever technique we are using. Okay. Now, in general, methods with these multiple roots of the characteristic equation are not preferred, and hence several methods with single roots are later found out, okay, for the characteristic equations. Let us see one example in order to understand how do we actually evaluate the correct root and understand whether the technique is stable or not. So, let us obtain a characteristic equation of the following algorithm. This is the algorithm that's given to us, and study its stability. And the algorithm that is given here is basically similar to the explicit method, but this is known as a midpoint rule. Okay, where what happens is we can compute yn plus 1 with the help of yn minus 1 minus twice of yn prime. Okay. So this is also an explicit expression. And what we'll do is, let us apply this simple equation that we have been dealing with, that is dy by dt is equal to lambda y. And if we just expand this and write, then this is going to be yn plus 1. This is going to be yn minus 1. And plus 2 times 2 h's again there, and we have to just replace this term, right? This term is yn prime. So yn prime is your lambda yn, so that has been replaced. Okay. Now let's substitute as we did the substitution previously, that is for yn plus 1, for yn, and for yn minus 1. Okay. So that is going to be C into mu times mu n plus 1. Again C into mu n and C into mu n minus 1. Okay. Now let's substitute in the above expression. And if we substitute these values in this above expression that we had written, this one, so we are going to get C mu of n plus 1 is equal to C mu of n minus 1 plus 2h lambda C mu of n. Okay. Now all the common terms, that is C's, get cancelled. Also, the mu values are taken common and removed. So what we basically get is mu square is equal to 1 plus 2h lambda mu. Now if you rearrange this, you will see that this is a quadratic equation and it can be written in the form of mu square minus 2h lambda mu minus 1 is equal to 0. Now, since this is a quadratic equation, it is simple to understand its root, which will be given by the formula for roots of quadratic equation. And we get it as h lambda plus, so h lambda plus minus root over b square minus 4ac, right? So that is going to be 1 plus h square lambda square, the whole root over. Now, so this is how the roots have been written, and the general expression of the solution is going to be yn plus 1 is equal to c1 times the first root n plus 1 plus c2 times the second root n plus 1. Okay. However, since we are solving for y dy by dt is equal to lambda y, we know that the true solution is just y equal to y naught e to the power lambda t, which again has one exponent. But again, we have these two different values of mu, which shows that there are two roots. But there shouldn't be, there should be just one root. Now, let us take a look at what is this mu1 and mu2, and how does these two values, mu1 and mu2, the mod of mu1 and mu2, vary with respect to h lambda, because it is important to understand here that if the mod of the true mu, the solution just has one root, right? So one is spurious and one is true. So if the mod of the true is greater than mod of the other one, then this algorithm can still be used for computing the solution of this ODE IVP. Okay. Now if we plot mu1 and mu2 for this particular case, if you compute these values and if you plot it, you will get a particular value, and with if you vary the h lambda value from 0 to 5, I mean from minus 5 to plus 5, this particular h lambda value, if you take from plus 5 to minus 5 to plus 5 and you have set of data points, and if you plot it here, you will see that the true mu value is the mu1, because our equation was y is equal to y naught e to the power lambda t, which shows exponential increase. Okay, and this is the one which shows the exponential increase. This is the one which is showing decay. Right? Now the true solution corresponds to mu1 because the value is increasing as lambda is increasing. Okay. Now, this method will give us the true solution only if this particular true value is greater than the other one, for h lambda greater than 0 for this location, or when simply lambda is greater than 0 because h is positive most of the times. Okay. So let's see what happens when we are computing the value in this region or in this region. So what we'll do is basically see the solution or see a few graphs for when the lambda value is positive or when the lambda value is taken as negative. Okay. So this can be done in MATLAB. Here I will be showing you the results of what might come if we simulate this thing. I mean, if we run this thing in MATLAB. So we will be seeing two cases over here. where we will see a positive lambda value and a negative lambda value. And let's start with a larger value of h. Okay, so let's first focus on this case where we have a positive lambda value and h is equal to 0.1. In this case, if you see, what is happening is, if the blue one is your true solution, not if, the blue one is your true solution, and the orange one is the predicted solution, by whichever technique uh, you've used for computing the solution for the ODE IVP. If you see this case, it mostly follows the trend of the ODE, of the actual Y value, but it is slightly different, right? Because of the time step. But if you, okay, now let us see the next one. But in case we decrease the time step, that is decrease the H value, what we see is it mostly merges. Okay, so here we are trying to get to the point that for lambda value, for a lambda value that is 5, for a positive lambda value, this graph tends to merge to the true solution based on whatever time step we are taking. If the time step is accurate, then it will merge. If the time step is not accurate, then it's not enough close to get to the true solution. But let's see in that region where the lambda value is negative. That is, we are trying to look at this region. And this was the region where mu2 was existing. Okay, so this kind of gives us an idea that mu2 is not the true mu, because it exists in a region that gives us unstable solution. Okay, so mu2 is not the true one. Now, if you take a lambda which is which is a negative value, that is -5, and you compute it for a time step of 0.05, which is even more accurate as compared to 0.1. Even in this case, if you see, if the true solution is supposed to be almost at 1, but the predicted solution stays around 1 till a particular instant, that is like till 1. But after that, it completely diverges and does not come to the true solution. Okay. Similarly, again, when lambda value is negative and we use a better h value, again it stays mostly close to 1, but it again diverges. Hence, this shows us that this algorithm will work for a positive lambda value. That is, it will work for this region, and in this region, whichever mu exists is the true root, but it will not work for a lambda lesser than 0 or a lambda negative. That is, in this region, whatever exists is not the true mu. Hence, we can conclude that the solution is stable in the region where mu, the true mu, is greater than the other mu, whichever other mu we have computed. Okay? So, this is how we basically understand whether a particular technique is stable. And it can be used in order to compute the solution for a particular ODE IVP or not. Okay, so most of these techniques that we have seen, the explicit, the implicit technique, this stability can be evaluated for all these techniques, and we can see whether, if we are using all these techniques, how stable or how do we expect the solution to merge or come close to the true solution. Okay, so that is all for today's class, and if you have any doubts, write to us in the doubt forum and we'll get back. Okay, thank you for attending, and we'll see you for the last week. The next class is basically the last live class that we will be having, so we'll see you there. Okay, thank you.